Do you want to excel in maths and science? If your answer is yes, then let me tell you go ahead with Infinity Learn courses. And to get best discounts, subscribe right now. The link is given below in the description box. Hello my dear students, welcome to my channel, and as you all know that I'm Divya, your chemistry expert, and today in this session we are going to do very interesting and important topic. Now let me tell you that the topic that we are going to discuss is from chapter chemical bonding. And before we go ahead to the main topic, I would really like to share with my students that if you go and buy the course, then please do not forget to use my coupon code, which is DE10. And you know that after using this coupon code DE10, you are going to avail 10% extra discount. So hurry up, don't miss the offer. So today the topic that we are going to discuss is very important, and it will let you know that why and how two species enter into a chemical bond. I hope you all want to know about it. So you know that covalent bond is formed by mutual sharing of electrons. We all know that this, right? But why exactly, the species, they have to form or they enter into a chemical bond formation. Particularly, we can say that how this bond formation occur and what is the necessity for it. So let's start, and it is none other than the valence bond theory, which is commonly called as VBT. So this theory explains us that why and how species they enter into a chemical bond formation. As you can see here on screen, I have shown you that we have two hydrogen atoms, and these atoms, you know that when we are talking about atom, then all the atoms, they have atomic orbitals, right? So here it is shown that the atomic orbital of hydrogen, that is 1s, combines with another atomic orbital of hydrogen, same, that is 1s, and this is how the combination occur, and it gives rise to a molecule which is H2. Okay, so this we are going to take up in this particular video. So now let me tell you that whenever any atomic orbitals, they enter into bonding, then there is no change that takes place in their shape, or you can say that their atomic orbital shape remains the same. For example, in this case, as you can see that we have taken the s orbital, and s orbital is spherically symmetrical. So before bonding also its shape is same, and after bonding also you can see the shape is same. So you need to remember this. You can just pause the video right here and note it down that whenever bonding occurs, so the atomic orbitals which enter into bonding, their shape remains the same. Okay, it is very important to note this. Okay, so postulates of valence bond theory. As I already told you that this theory is here to explain that why and how the species enter into a chemical bond formation. So there are certain assumptions, right? So first postulate of this valence bond theory is that atoms do not lose their identity even after bonding. For example, if hydrogen molecule is formed, we know that it is formed by the combination of hydrogen atoms. So the identity of an atom remains same as it is before the bond formation. So after bond formation and before bond formation, the identity remains totally exactly same. Second postulate is whenever a bond is formed, it is always formed due to interaction of valence electrons only. We know that whenever a chemical bond formation occurs, then the electrons participate, and only the valence electrons, they participate. That is the electrons which are present in the valence shell, and the electrons which are present in the inner shells, they do not participate. So inner electrons, they remain unaffected. Only the valence electrons participate. Only the valence electrons lose their identity in the bond formation. And also very important to note that stability of bond depends upon the amount of energy released. This we have already discussed in one of the video, that when two species, they approach together to form a bond, then what happens? They are approaching, right? They stop at certain particular distance where the bond formed between them is quite stable. And how we come to know that the bond formed is stable or unstable? See, a state of minimum energy always imparts stability, right? the state of minimum energy always corresponds to a maximum stability. So if the amount of energy released is more enough, then the bond formed is always stable. So stability can be, known by just, measuring the amount of energy which is released. Now, I told you that whenever the atoms, they are approaching, right? They keep on approaching and then they stop at certain particular distance where the energy is minimum, right? Where the energy is minimum and stability is maximum. And that particular distance is called as an internuclear distance, which can be also called as bond length. For example, in this case, you see that A and B, they both are approaching, but they stop at certain distance. And that particular distance leads to the formation of bond, and that is a internuclear distance, which we can call as bond length, because this is a particular distance where the stability is maximum and energy is minimum. And at this particular distance, the bond formation takes place, because we want that whatever the molecule is formed, it should be stable. And it will be stable only and only if the energy is minimum. So do remember this thing, very important, that whenever the atoms are approaching, two kind of forces operate between them. Two kind of forces, one is attractive forces and the other one are repulsive forces. And you will see that I'll give you one example and you will yourself feel that whenever the attractive forces are more in magnitude as compared to a repulsive, only and only then the bond formation will occur. And if in case you see that repulsive forces are more as compared to attractive, then no bond formation will occur. Remember? So remember this and note it down that whenever attractive forces will be more, only then the bond formation will occur. Otherwise, there will be no bond formation. I'll give you one example. Now let's see the formation of hydrogen molecule. So for example, I have two hydrogen here. One is HA and let's take another as HB. Okay, we know that hydrogen has got one electron and one proton in it. Let's say these are the electron and proton of this hydrogen HA. Let's take it for HB also. Let's say that electron of HB is EB and proton of this second one is PB. Now, if you'll see the attractive and the repulsive forces operating between them, then you will come to know that that both the electrons, they are negatively charged. So both of them, like when the atoms will approach, they will show repulsion between them. So this is going to be one sort of repulsive force. Same proton and proton will repel each other. Okay, so that means the repulsive forces here will be between EA and EB and PA and PB. Okay, now let's see and count the attractive forces. Now here when they will approach, this electron will be attracted by the proton of the other hydrogen atom. Same way, this electron of B1 will be attracted by proton of the A1. And also there is an attractive force between electron and proton of same atom as well. So how many attractive forces? 1, 2, 3 and 4. So you get to see 4 attractive forces. And how many repulsive forces? Just 2. So which kind of forces predominate? Obviously attractive forces predominate. And I told you that whenever attractive forces will be more, then only the bond formation will occur. That is the reason when hydrogen atom they approach each other, their atomic orbitals overlap, and because the attractive forces magnitude are more as compared to the repulsive ones, the bond formation occur and hydrogen molecule is formed. Now same way, if you'll focus that why helium molecule is not formed, I'll give you one example for this as well. Let's take this as helium A and let's take this as helium B. Okay, we know that helium has 2 protons and 2 electrons. So let's show it like this. Let's say that 2 electrons, let's put it A1 and A2 and 1 proton, 2 protons. Let's put it again A1 and A2. Same way if you'll write here, it has got 2 electrons and same way 2 protons. So if you'll count the attractive and the repulsive forces here, in this case, you will find that the attractive forces as compared to repulsive forces are less. Here in this case, repulsive forces predominate, and that is the reason helium molecule is not formed. Okay, that is the reason hydrogen is formed, because attractive forces predominate in that case, and here helium molecule is not formed. Okay, I'll tell you how to count it. You can see that here in this case, this will repel electrons, even these electrons will repel, even like there'll be a repulsion between electrons and proton. And same way, if you count the attractive forces, like the number of the forces will which come out to be very less as compared to the repulsive one, and that is the reason helium molecule is not at all formed, but hydrogen molecule formation is possible. So you can always count the attractive and the repulsive forces, and it will give you an idea that which bond formation will happen and which will not happen. And one thing is very important to note, that whenever the two atoms they approach to form any molecule, so how the combination occur, how they combine, overlapping of atomic orbital is mandatory, right? So overlapping of atomic orbital always result in the formation of chemical bond, and the electrons are localized in the bond region due to overlapping. In this case, for example, you know that in case of hydrogen, we have got two s orbitals. So they overlap, and that is the reason, H2 is formed. Now, let's talk about the overlapping of the orbitals. How will you define it if somebody asks you? It is defined as partial merging of bonded orbitals. Partial merging because they are merging into each other. So, partial merging of bonded orbitals. And if the overlapping is more stronger is the bond, right? If there will be more overlapped region, that means they are held strongly. Therefore, the bond formed will be stronger. So, two kinds of, depending upon the overlapping, two types of bonds they are seen. One is sigma and other is pi bond. Sigma bond is formed when there is head-to-head overlapping, and pi bond is formed when there is sidewise overlapping. One thing you always have to remember, only those atomic orbitals can overlap which are symmetrical about their internuclear axis. I'll show you how. So sigma bond, I told you that it is head-to-head overlapping. So this bond formation is possible only when two s orbitals combine, or one s and the other p combine. And this p should be the one which is on the z axis, not the x or the y one. Okay, always the z axis one, because it is symmetrical about the same z axis. So now when two s orbitals they combine, you see that they overlap head to head, and this kind of s is overlapping, that is sigma bond is formed. Even s can overlap with p, but only pz. Okay, then they can overlap head to head, and sp overlap is formed. Again, that means sigma bond is formed. Sigma bond can also be formed between two p orbitals, but those p orbitals should be symmetrical about their internuclear axis. And sigma bond formation is possible only if two pz orbitals they combine. It cannot happen between px or pz, or py or pz, or between px or py, because they are aligned on x and y axis, right? And in case of sigma, the mandatory thing is that is head-to-head overlapping. So only pz and pz, when they combine, they can show head-to-head overlapping, and other three combinations are not possible for the s sigma bond formation. Okay. Now talking about the pi bond, I told you that it is sidewise overlapping, and it is possible only when two p orbitals they combine, maybe two px, maybe one px, py, they can combine. This is how you'll show the sidewise overlapping. See how they are being overlapped. One is, and it is sidewise merged into one another, right? And even we can represent it two ways, because the electron density is more above and below the plane. So it can be shown this way as well. Now, if I ask you that which bond is stronger, sigma or pi? First thing, tell me which out of them denotes the sigma bonding. Yes, the second one, because head-to-head overlap is the sigma bonding, and when two s orbitals they combine, they show only and only sigma bonding. And this one is a sidewise overlapping, which indicates the pi bond, and this one is sigma. Now, in both the cases, you can easily make out where the overlap region is more, in the first one or in the second one. Of course, it is in the second one. That is why sigma bond is much stronger than the pi bond. Because more is the overlapped region, stronger is that bond. Now let's talk about hybridization. See, whenever the atomic orbitals combine, they are basically intermixing of the orbitals that occur. Right? Intermixing of orbitals so that they can redistribute their energy and they give rise to new set of orbitals which are similar in energy and shape. Understood? That means overlapping of, or you can say intermixing of orbitals of slightly different energies, right? And when they overlap, they redistribute their energy. Equal energy distribution occur, and after that the orbital which is formed, right, they have got same shape and same energy. So there are different kind of hybridization, like you have sp hybridization, you have sp2 hybridization, you have sp3 hybridization. So more is the overlapping, right? More is the overlapping, stronger is the bond. So overlapping of orbital take place which have same energy. And in case of orbitals which have different energy, they can't overlap. You have to remember these things while doing the hybridization. I'll give you one example. For example, if I say, if we talk about s and s orbital, we know that they can overlap, right? The combination is not possible between s and px. Like if s tries to combine with px, this kind of combination is not possible. Also, you need to remember that number of hybrid orbitals are always equal to the number of atomic orbitals that combine. Right? If three orbitals, atomic orbitals are combining, then the hybrid orbitals will also be 3. Right? And all the hybrid orbitals, that is the orbitals after intermixing of energy that is formed, they are equal in shape and energy. Hybrid orbitals, they are more effective in forming bonds as compared to the atomic orbitals. And hybrid orbitals, they always direct towards, the specific directions in space, so that gives the proper and perfect geometry to a molecule. I'll give you one example to explain it. Let's talk about sp hybridization. So sp hybridization, where one s orbital and one p is participating. Let's talk about beryllium fluoride, which is BeF2. So here the central atom is beryllium, and you know that atomic number of beryllium is 4. So if you write its configuration, it is 1s2, 2s2. We can show it like this also. This is 1s, and here this is 2s, and 2p is empty. Okay, 2p is empty. Now this is the ground state configuration. Now if we show the excited state, then we can move it to this place. So in excited state, we can represent the configuration in this way. Excited to this, right? Now when fluorine approaches, you know that the fluorine atomic number is 9, and if you write its electronic configuration, it is 1s2, 2s2, 2p. You have 4, 5, 6, 7, 8, sorry, it's 5. Okay, so when it approaches, they can easily, these orbitals are available, and this case, the kind of bond formation occur. So here one s and one p is participating. So therefore the hybridization is said to be sp hybridization. And I told you that always the hybrid orbital, they direct them in the preferred direction in the space, and which gives the geometry to a molecule. So here in this case, the geometry is linear and the angle is 180. So always you can show the hybridization this way by writing their configuration, ground state, excited state, make those orbitals available, and then you will yourself come to know that which type of hybridization is present in them. And accordingly, you can comment on the geometry and the angle they will have. So with this, we have come to an end. I hope you have understood the concept of VBT and also about the hybridization and of course about the overlapping of the atomic orbitals. So please stay connected if you want the quality content. So one thing more, if you haven't subscribed my channel, you can just subscribe it right now. Thank you. Take care. Bye-bye. Have a nice day.